Hello again. We're up to chapter 25 for our trek through the universe, and we are up to the Milky Way, and hence I have the picture that's up here. We are going to talk about our local galaxy, the one we're inside, and because we're inside of it, we can only see it from the inside. To get a good picture from the outside would require going a long way out and turning around and looking back in, and then sending the image back to us at the speed of light, and all of that would take a round trip of about 100,000 years. So that's job security. You could probably work from home, just like most of us are doing right now if we're lucky enough to continue working. But I don't know if that would be the best use of anyone's time, and I'm not sure that even with modern medicine, we're going to keep anyone alive for that length of time. So we have to do the best we can. One of the things that we'll see as we look at this chapter is there's a history of how it evolved and developed. So let's go ahead and get started. I will see if I can share my screen here with you, and we'll get on to our slideshow. Yes, does it want to give me the slideshow information? There we go. Play from the start. And I'm up here in the corner as well. So I'll keep this. I have asked a couple of you if you want me to keep my image in the corner here, or if you want me to not have it. Most people seem to want it in there, so that's fine. I find I keep looking to the side because from my image of the camera, it's actually over here. So I'm sort of looking off to the side, and I'm sort of looking at myself. If I put it here, I'm looking at myself now, but I'm also covering part of the screen. So I don't have a good solution for that. So I apologize if I don't always seem to be looking directly at you. But the Milky Way is the collection of stars that we're in. There are probably 200 to as many as 400 billion stars in our galaxy. We see from the inside this sort of patchiness of gas and dust and stars. For a long time, people thought that was simply gas and dust because, as we see with the naked eye, that's what it looks like. When we began to use telescopes in 1609 forward, aiming it at that patchiness makes it resolve into more and more and more stars. So when we look at things that are clumped together, often the light bleeds together, and that's what gives us this effect. We can see the Milky Way pretty much from everywhere on Earth at different times, at different angles, depending upon where we are in terms of the daytime or nighttime, as it were, and where we are seasonally as we go around the sun. The Milky Way is a barred spiral galaxy. Essentially, I grew up in a spiral galaxy, and we still refer to it as a spiral galaxy quite frequently because the bar in the middle is rather small. And in our next couple of lectures, we'll talk about what it means to be a spiral galaxy and it means to be a barred spiral galaxy. So we're a few hundred billion stars. That number sort of keeps going up over the course of the last 100 years or so. When I was taking 101 and 102 level classes, we thought that our galaxy had about 100 billion stars. Now we're edging from 200 to 400. But a lot of those that we keep finding are smaller and dimmer, so they were harder to locate. We're all held together by mutual gravity, and at the very center, we have a supermassive black hole. But I'm getting ahead of myself here. All of that stuff is stuff that we've discovered later. For a long time, of course, people thought that everything went around the Earth. We call that the Ptolemaic or geocentric model. Everything's going around the Earth. Then Copernicus came along. And there were some people before Copernicus who had this idea, but he's the one who really sort of systematized it and made it what it is, said the sun is in the center. That started happening in the late 1500s, where people began to think of the sun as the center. And for a long time, really up until about 150 years ago, so not that long ago, people thought that, okay, the sun is in the center of the solar system, but the sun is also in the center of the entire universe. And the entire universe is, in fact, just one big collection of stars, our galaxy. Some of the people who began to put shape to the galaxy we live in include the Herschels, William and Caroline Herschel here. They came from Germany. Of course, the royal family in England came from Germany at that time. He was a musician, but in his spare time, he was an amateur astronomer. He eventually became so good at it that that became his profession. And it was the one who discovered the planet Uranus. When you think about it, he was the first person to really discover a planet, because Mercury, Venus, Earth, Mars, Jupiter, and Saturn had just sort of always been there since before history. We could always see all of those. And it took the telescopes that he had to figure that out. And then he began to look at other stars and comets and other things. His sister Caroline was a great, great help along the way. And they made their own equipment. They made their own telescope mirrors and other kinds of things. Caroline was one of the first women to be honored as a professional astronomer and professional scientist in her own right. When I went to England just a few weeks ago, one of the things I insisted that we do is go to the Herschel Museum, which is in Bath, a city called Bath because there are Roman spas there that were called baths. This over here is a replica of the telescope that he used to discover the planet Uranus. So you see, not very large. You don't need, I have actually a better telescope than this in my office at Ivy Tech. But of course, I don't need to discover Uranus because it's already been discovered. This is a plaque in the backyard, the garden of his house, that commemorates that. Also the commemoration of the fact that he helped discover infrared radiation. I'm standing over here on the spot where his telescope was when he discovered the planet. And this booklet here is one of his notebooks where he was talking about how he was mapping out where all of the stars were in the sky. And as he looked at the stars, some are brighter, some are dimmer, some are closer, some are further away. This took us a while to figure out that there are both dimmer and brighter stars. We've talked about that before, and some are closer and some are further away. We've talked about that before. But he still had the idea that the sun was somewhere near the middle of all of this, which sort of makes sense because he can only see stars that are within a certain distance of us. Even with that telescopic equipment, we can only see a certain patch of our solar system's neighborhood. And so it looks like we're mostly centered, except notice we're beginning to see a flattening here. He noticed that there were more stars in certain directions than there were what we would consider to be up and down in vertical ways. So this began to plot out what our Milky Way galaxy looks like, that it is flattened and it seems to be moving around. That was another thing that was there. But of course, they still had the idea that the sun was in the center. That took a while to displace. One of the persons who helped displace that is this guy named Kapteyn, and Kapteyn was someone who used sort of the counting stars, just sort of going out and counting in each area of the sky, where things are here and here and here and here and here. And he was able to refine the Herschel idea that we are a flattened disk and that we in fact go a long, long way out, kiloparsecs. Parsec is a sort of a complicated thing, but think about it as a little over 3 light years. So if we're 10 kiloparsecs, kiloparsec is 1,000 parsecs. So 10,000 parsecs or 30,000 light years across. That's getting really big. Because before then, the universe, just a few hundred years before this, was just around our solar system. Then it was getting bigger and bigger and bigger and bigger, almost beyond belief bigness that we have here. Is bigness a word? Okay, we'll go with that. But he began to use photography that could use sort of time exposures that would bring out a lot more stars than simply looking through a telescope. That's one of the difficulties that people have to this day of looking through telescopes. If you just put your eye up to the telescope, you're not going to see anywhere near what you will see on a time exposure. And William Herschel and his sister Caroline did not have that option. Photography was not there. But what it also began to pick up was the sort of the gas and dust that we have in our galaxy. And part of the problem with the gas and dust is it generates a a phenomenon called galactic extinction. And when we use the word extinction, we're not using it in the sense of like the extinction of the dinosaurs. Think about the word extinguish. That means to put the light out. So if we're talking about extinction, it's putting the light out as light comes from the distance. And you can even see in the little picture of me that there's some gas and dust off to the side of me over here. The light behind that is being extinguished. Because the light behind it is going through the gas and dust and not getting to us. So we call that galactic extinction. And Kaptian here began to understand that that was an issue that was taking place. So it took us a while. Then roughly 100 years ago, Harlow Shapley came along and he began to look at globular clusters. We've talked a little bit about globular clusters before. They're collections of thousands or tens of thousands, very occasionally maybe 100,000 to 1,000,000 stars, but they're clumps of stars that move around the galaxy on their own, separate from the disk, separate from the arms and other kinds of things. So he began to look at these and he noticed that they all seemed to be going around a certain point along the way. And the sun, see, this is Herschel's old mapping of our galaxy. Shapley noticed that we have these globular clusters much further out. We have them top and bottom. We also have them extending a long, long way away. Because they're clusters of thousands and tens of thousands of stars, they don't get affected quite as much by that galactic extinction that we had. They're affected to a certain extent, but not quite as much. And you can see here the sun is actually pretty off-center from where the center would be for all of these. And of course, Shapley knew he wasn't getting all of the globular clusters all together. So what he figured out was that the center of that was probably quite a bit away from where we are. He actually overestimated it. We're actually about 25 to 30,000 light years away from the center of our galaxy. Remember, close is good in astronomy. He sort of overestimated that, but he concluded properly that the center of where all the globular clusters seemed to be moving was in fact the center of the galaxy, not our sun. And of course, when we look at it today, we see there are all sorts of globular clusters that are moving around. We are inside a flat disk that has several arms. We have at least 4 arms or armlets. We are in fact inside what's called the Orion spur of one of the arms that's there. When we look at other galaxies from beyond our own galaxy, we can see some spiral forms like this one here, M74. We can also see some barred spirals here, like NGC 1365. Remember, M stands for the Messier catalog, NGC stands for the New General Catalog. We again have Herschel, my guy in the museum, there to thank for the starting of the cataloging process. And we continue that to this day using his methodology and his inspiration and some of his basic beginning research. When you're looking at a galaxy from the inside, it's sort of hard to tell how the center looks because we do have all of this gas and dust and we have other issues with things lying between and interpreting the data. So it took us a while to figure out that we have a little bit of a bar. This is actually an extreme bar here. It goes way across. We have just a little bit of one. So we can be forgiven for not understanding that we were in a barred spiral. As I'd like to tell people, I was born in a spiral galaxy and now I live in a barred spiral galaxy. When I was born, there were 9 planets. Now there are 8 planets. So there are all sorts of different kinds of changes that take place. If we look at an interior picture of the galaxy, this would be one of the ways in which we look at it here. This is an infrared map. This is taking the lower energy level light that's coming off of stars and mapping them out. We can see gas and dust through the middle. We can see most of the concentration in the disk here, a large concentration in the bulge here. This is a 360-degree kind of view, so we would actually have it like wrap all the way around. if we could do it 360 degrees. So this would be in the direction here of Sagittarius, and we would be able to map out the other constellations around here. Notice it gets less and less as we go up and down, as we're looking at the polar regions. But here are the major parts of our galaxy. We have the center, as I mentioned before. We have a supermassive black hole there, and we'll talk a little bit more about that later in our semester. I'll probably talk maybe a bit more about it before the end of this lecture. We have a disk that goes around. We have a thin disk which has clusters of stars. We have a thicker disk which is less densely populated. We have our halo of sort of gas and dust, as well as our globular clusters. And then we also have a lot of dark matter that's in the bulge, in the halo, and variously around our galaxy. We can't really represent that well because we don't really know what it looks like. But the Milky Way has been a sort of a mythological inspiration in many different cultures. We've had different ways in which the Milky Way was formed or was presented along the way. One of the ways in which it was supposedly formed was from basically the mother's milk of a goddess that streamed across the heavens. They don't talk about that too much in high school because it becomes problematic to talk about such things. But here would be a good representation based on the data that we have now from various types of surveys of stars, including Hubble, including the Spitzer, which I talked about a little bit earlier in our semester, that was just decommissioned earlier this year after doing great work along the way. We have two major arms. We have the Scutum Centaurus arm here, and we have the Perseus arm here. So notice those two are directly attached to our bar in the center around the bulge. And then we have some minor arms that are also coming out there, including our Orion spur here, which is just inside the Perseus arm. We're quite a ways away from the center, but that's actually good for us. This is where we are in terms of a projection in our galaxy. Because if we were closer to the center, there would be a lot more radiation, and that's not good for us. So it's a good thing that we're in the rural district. Here we can see that the sun is located in the Orion spur, roughly about here. The Orion Nebula is sort of on the outside, away from the bulge, away from the center of everything. The Crab Nebula is over here. Cygnus X1, which is one of our black hole candidates, is over here. So notice that most of the things that we see, even with our best telescopes, tends to be in this small area of our galaxy. So the further away we are, especially if we look towards the bulge, there's just too much in the way to see things. If I go back here, see, this is where we are. Trying to see things on this side of the galaxy, well, good luck, because there's way too much in the way. There, we can get a little bit of evidence here and there in radio and a few other wavelengths, but for the most part, we're never going to see from our position here anything in the visual light range, for example, because it's all going to be blocked and extinguished before it gets to us. There are different ways in which the galaxy formed its spiral arms. Perhaps the best model of that is sort of the motions of the galaxy, the particles in the galaxy, including gas and dust, all the way up to major stars. They would be considered the particles of the galaxy as well. Over the course of time, they sort of spin, just as most things in our universe are moving, most things in our solar system are moving, and the gravitational influences are at work here. Many galaxies have spiral arms, and they are a not uncommon feature for a lot of things. But as we're going through our galaxy, as stars go around, we take about 250 million years to go around the bulge from where we are. We're also going up and down. We have this oscillating pattern. So I often tend to think of it as, if you remember vinyl records, as vinyl records are going around, if you leave a vinyl record out in the sun, which I did a couple of times when I was a child, because we had a pool and I set up my record player and the records were out there, and of course the sun's down, and then you put the record on and it's up and down, and it's like that's what happens to our stars as well. So if you feel like things are going up and down in your life, you may just be responding to the motions of the galaxy here. All of the stars in the disk are moving around, so all of them have their own motions. They all influence each other, and they're all mutually attracted to each other, which is what helps keep the galaxy together. We have, as I mentioned before, 200 to 400 billion stars. And that gives us a huge amount here. This is 10 to the 11th power. So that's a 1 with 11 zeros following it. So we're getting into the multiples of trillions of times the mass of the sun by the time you put all of these stars together. The material that's in the disk also goes around. The gas and dust, we call that our interstellar medium. Remember from earlier lectures, we talked about that before. We have a lot of big blue stars. Those tend to burn themselves out rather quickly. Remember our lectures on stellar life cycles. We have lots and lots of larger stars that will blow themselves up and return their materials out into the gas and dust. And as they do that, they are in fact giving back the material that they've created inside their fusion reactors. So we call that metallicity, which means each time one of those explodes, it puts out more and more higher elements. And in terms of astronomy, whenever we're talking about metallicity, we're not just talking about lead and iron and gold. We're really talking about anything bigger than hydrogen and helium. It's not a chemical definition here, it's an astronomical definition here. So carbon would be a metal, oxygen would be a metal in terms of the metallicity that we're talking about here. So as we look at these, as they're sort of going around in our disk, they are called population 1 stars. Those are the ones that are building up the elements that are there. Some galaxies are pinwheel shaped that have a really tight structure. We'll see this when we look at other galaxies along the way. Sometimes they have bigger bulges, sometimes they have smaller bulges. Some of you may have done the galaxy hunt in Zooniverse and galaxy identifications, and one of the things that they would often ask you would be, does this galaxy have a well-defined bulge? Does it have a faint bulge? Does it have no bulge? Does it have major spiral arms, or does it not have? So there are different forms that these can take. But as things are going around the center of the galaxy, just sort of like Kepler's rules, we have the structure of the galaxy in the way in which the further things are away from the center, the slower they should be going. Just like Mercury goes around the sun much faster in 88 days than Pluto does in 250 years, and the further out you get from the sun, the slower it goes. When we're looking at the rotation of our galaxy, we should be getting slower and slower and slower, this blue line here, as you get further and further from the center. We have this sort of up and down here because there are concentrations and clumps of material that are influencing each other. But as we get further and further away, it thins out, and so it should be going slower and slower. But in fact, what we see is this red curve up here, where it looks like we are in fact going faster. What's causing that? Well, there's nothing that we can see that's causing that. And that's the issue. Vera Rubin is one of the persons who figured out that something's out there pulling on it, and that something out there is something we don't see. That's why we call it dark. But since it's something that has gravitational pull, we call it matter. So hence we have Vera Rubin here to thank for our mysterious idea of dark matter. Outside of our major concentration of stars in the disk, we also have our globular clusters, as I mentioned before. Here's one particular one that you can sort of see would be going around at a different way, as our major population of 1 stars would be going around in the disk. And globular clusters can go every which way around the bulge. But they tend to be older stars. They tend to be reddish and lower energy stars. They are in many ways older than most everything else in the center of our galaxy. We know of at least 150 of those. The number sort of goes up and down. Mostly it goes up as we discover new ones along the way. But they tend to be lower in metallicity. They don't have a lot of big, bright blue stars that are churning out more and more material. They tend to be smaller, long-lived reddish stars and yellow dwarf stars like our own star. So we call those population 2 stars. And when we look at the rest of the halo, if we sort of go out, I'll take you back here for just a moment. So we're looking at the halo here. We keep finding more and more stuff in the halo. And one of the things we've found quite a lot of is X-ray material. We have lots and lots of gas and dust that's out there, particularly gas, that is very, very hot. Now, there's not a huge density of this. You'll actually have less density in the halo than you would have, say, hot air inside of your oven. So even though it's superheated stuff, there aren't a lot of particles that are out there. The globular clusters sort of swoop through these kinds of things, but because of the way the gas and dust is superheated, it's not falling in under its own weight. The energy keeps it apart, so gravity doesn't take over. So we don't get a lot of newborn stars the way we do inside the disk. So population 2 stars are in the halo. Lower metallicity, that means they're almost exclusively hydrogen and helium that's there. That tells us when they were formed in a pristine environment. That means basically there was only hydrogen and helium there to start with. And that's what the whole universe started with. So when we're looking at the globular clusters, we're looking at some of the earliest parts of the universe. Then as we look towards the bulge, we see that there are lots and lots and lots of stars, very high density. Cubic parsec, again, that's a little over 3 light years in one direction, another direction, and another direction. 1,600 stars. Whereas when we're out here in the boondocks, we're going to have 1/10 of that at best. Maybe even less in some areas. So the night sky may not actually ever get dark in some of the areas here around planets that are in the bulge. The other problem with that, of course, is the planets may get ripped away from their stars because of the gravity of other stars. So we might have a lot of rogue planets. We do call them rogue planets when they're out there on their own. We also have a lot of gas and dust that's held in there. And the bulge itself is sort of separate from the rest of the galaxy. It is its own thing along the way. So the bulge has its own gas and dust. It is forming stars. That's one of the things that's different from the halo. And when we're looking inside of this area, because of the galactic extinction that I've talked about before, we're mostly looking at it in radio waves. We do have a bar across, and when we're looking for that kind of stuff, again, we're often using radio technology. We can also see some in infrared, but we tend to look a lot in the lower energy levels. This is a radio image of our galactic center. We have the sort of center of the galaxy that's right here. This is from the Very Large Array. Again, if you've seen the movie Contact with Jodie Foster and Matthew McConaughey, they have a portion of that at the big collection of disks that are in New Mexico here. We can see some different objects that are along the way, including this one here. This is Sagittarius A asterisk. That is our supermassive black hole at the very center of our galaxy. And it is 2 to 4 million times the mass of our sun. It's not one of the larger supermassive black holes by any means in our universe, but it is ours, and it's the largest object, single object in our galaxy along the way. Again, here's the Milky Way as we're sort of looking at the gas and dust and stars in the disk. We can see other areas of stuff, interstellar medium and energy. Spitzer was one of the ones who took the lead in looking at the universe in different ways. the Spitzer telescope, which I've mentioned several times because, of course, in February, it just finally went offline after being a workhorse for about a decade and a half. In many ways, it was more important than the Hubble. The Hubble got all the glory, and of course, the Spitzer did a lot of the work. Not that the Hubble doesn't do work, but it's telling that the new telescope that's about to go up next year, the James Webb, has more in common with the Spitzer than it has in common with the Hubble, because this is a very important area. As we're looking at this stuff, we can see through some of the gas and dust, and we can see past some of that galactic extinction. And as we look towards the very center of our galaxy, we see that it's maybe as much as 100 million times denser than the neighborhood in our own territory. So there are lots and lots of things that are in the center. There's molecular disks and rings of material that are circling the galactic center. There's a lot of new star formation, starburst, rapid formation. And some of these are very large, which means they live very short periods of time before they're returning their material out. We have these different questions. So I'll leave you to look up these in your textbook. What is the conundrum of old age? What is the paradox of youth? We're talking about stars, we're talking about gas and dust, and we're talking about something in the galaxy that's really old, but also seems to be really young. So you can look those up and see what kinds of answers you might get. Remember also, Google is your friend, but you'll see different answers to those. And this is part of the cutting edge of astronomy today when we're doing galactic astronomy. One of the things that I had hoped to do when I was way back when I had more hair here and a lot less around the middle, was I wanted to do galactic astronomy. And we know so much more now than we knew then. And it's one of those things where we have a strange geometry and a strange physics that comes forward. We can see one thing that's at a higher energy level from the center of our galaxy. We mostly look at radio waves and infrared waves, but that's X-rays. X-rays are at the top, whereas radio waves and infrared are all at the bottom of the spectrum in terms of energy. But we have a lot of X-rays being formed by the supermassive black hole, just in the way that the Cygnus X1 black hole alerted us to its presence. Our supermassive black hole, Sagittarius A asterisk, or Sagittarius A star, you'll often hear it's just called A star, has identified itself with streams of X-rays. And again, we have that probe, the Chandra X-ray satellite, because X-rays don't get through, fortunately, our atmosphere. So to see them, we have to go up above the atmosphere along the way. But we have sources like white dwarfs and neutron stars and regular black holes that eat material and generate X-rays. But when we're looking at the center of our galaxy, we have a huge source that's there. And as we get closer and closer to it, this is an image taken again from radio that's then sort of ported up into what we might be able to look at in terms of visual light. We have the bright spot down here that is Sagittarius A asterisk. And then we have some modeling where we're looking at the very center here. This comes from the Keck telescope. The Keck telescope is on the mountaintop on the big island of Hawaii named Mauna Kea. It's actually a double telescope with two different dishes there. But one of the things it's doing is it's tracking individual stars as they go around. And they're influencing each other, but they're also being pulled and tugged by this virtually invisible thing right in the center there. So what's going on if you have something that's influencing this many stars? See, these aren't planets going around. These aren't comets or meteors. These are major stars that are spinning around. Something huge is pulling on them. Something huge is keeping them in orbit and pulling them. So we've been tracking this for over 20 years and following what's happening there. Now, Andrea Gaze and her team are looking at these different kinds of structures and these different kinds of modeling, because it's in that we can then calculate how much is at the center along the way. And of course, you have all heard, I'm sure, of the super stuff that was done with the photograph of the black hole area. And that was from a nearby elliptical galaxy, relatively, in our universe nearby. But that black hole is much larger than the one in the center of our galaxy. The center of our galaxy is the next one up, and that's what I look forward to in the next year or two. Things go around that in the galactic plane. Our thin disk of stars goes around like that. Halo things go every which way around the galactic plane. Both of them are centered on the black hole in the center. As we look across our local group, our local neighborhood at the Andromeda galaxy, you can actually see this bulge as a fuzzy patch if you go outside the city looking towards the constellation Andromeda. It is the farthest thing you can see with the naked eye in the sky. It is over 2 million light years away, and it is also centered on a supermassive black hole. And you can note we've got a lot of older yellowish stars in this area. We've got some bluish stars, some high energy, younger bluish stars in this area here. So we have a sort of a collection of stars around the supermassive black hole here that is similar to ours. So we learn a little bit more about our galaxy by looking at our nearest neighbors. This is our nearest neighbor major spiral. It's not our nearest galaxy. That sometimes, if you're ever on Jeopardy and they say, what's our nearest galaxy? It's not the Andromeda galaxy. And if they count you wrong and say it is, then protest and you'll get on the show again, and then give me part of your winnings along the way. But how galaxies form, we saw a little bit about how the spiral arms can form, but it's sort of like a solar system, sort of like a planet. We have gas and dust that collapse under its own weight. Each particle, each part of material in there has its own intrinsic temperature and its own intrinsic motion that all gets regularized as things hit each other. Some things span out into globular clusters through various random processes that happen, but the majority of the material will sink and fall towards the center and turn into our galaxy as we see. One of the things that we can also note is that we're part of a collection of galaxies. As I showed you just a moment ago, the Andromeda galaxy is our nearest major spiral galaxy, but it has several smaller galaxies around it, its own little entourage, and so do we. This looks like we have some kind of demon that's barging its way into our galaxy. In fact, we are eating this galaxy along the way. We have eaten several galaxies in our galaxy's history. So has the Andromeda galaxy, and eventually the Andromeda galaxy and the Milky Way galaxy will merge. They'll sort of spiral towards each other. That's what's happening now. And they'll just sort of splat everywhere until they sort of converge into one massive monolithic kind of galaxy. But in the meanwhile, we're eating the Large Magellanic Cloud. We're eating the Small Magellanic Cloud. We can actually see streams of stars that are coming off of them as they rotate around us that we're pulling in. But not too long ago, we also found some clumps of galaxies that have already been eaten or are in the process of being eaten, like this Sagittarius dwarf galaxy. Not too far away from us, not too far away from the center of our galaxy, because it's actually in our galaxy. And these are stars that were actually formed outside of our galaxy and are still, through their own mutual gravitational pull, clumped together. Think about it in terms of if you've ever seen a snake eat a rat, and you can sort of see the bulge of the rat go through down until it's digested. This, as it enters the spin cycle, will eventually spin out, and the stars will just become part of the random processes and random collections of stars in our galaxy. But for a while, it will remain partly undigested, partly clumpy here, and it will retain some of its own galactic signatures. And we have found not only stars from other galaxies in our galaxy, but we found planets from other galaxies because they're around stars that are now in our galaxy. So as we look at what's happening in and around our galaxy, we see different galaxies that are being absorbed into ours, and we see streams of stars that happen, that some of which are still there as echoes of when the galaxies were merged into us. And of course, then we have the leftovers from the earliest times in our galaxy, the globular clusters. Notice the dominant color here tends to be yellowish, tends to be on the red side rather than on the blue side. We've got a couple of blue stars here. Those may be foreground stars. So they may be stars that are sort of in the way as we're looking at something much further away. This reddish star, this really bright red star here too, would strike me at first glance as being a foreground star. So what I mean by a foreground star is, imagine we're here and the globular cluster is over here, but we might have a couple of stars in between as we're looking at the globular cluster. So this globular cluster may have been the bulge of that galaxy that we are looking at as it's merging into us. And as we merge into the Andromeda galaxy, here's a sort of computer simulation. In about 3 billion years, our Milky Way galaxy and the Andromeda galaxy will be sort of close to each other in the sky. Here's us looking at our galaxy from the inside. Here's the Andromeda galaxy sort of moving in on us along the way. So what's happening here, and in fact, the gravity is beginning to pull on both of them already. So it's not just 3 billion years from now, suddenly something will turn on. Within 1 billion years, we'll begin to have some little streamers coming out from both of them as well. We're already being influenced by the gravity there. But as it goes on through its processes, 500 million to 1 billion years later, you'll see the spiral on both of our galaxy and the neighboring galaxies will all be disrupted and will become this huge sort of splatter galaxy, and we'll just sort of continue to sort of wrap around and wrap around and wrap around each other along the way. And we'll still get lots and lots of star formation as the gas and dust is pushed together and slammed together. That will help form more and more and more stars. See all the blue that's happening in here. And then the red is the supermassive stars beginning to explode and increase the metallicity that I talked about before. And eventually, we will turn into, most likely, a huge goose egg of a galaxy, an elliptical galaxy without any spiral arms at all. So we'll go from being spirals to being a big splatter, sometimes called an irregular galaxy, and then into a final sort of phase where gravity evens things out and we become a huge elliptical galaxy. Our planet may still be here through all of these processes, because this whole process may take anywhere from 4 to 6 billion years, and our sun we're expecting to last another 7 billion years. So get your cameras ready. It should be rather fun. Thank you for joining me for our galactic trip. I appreciate that. I especially appreciate being able to share what I was able to do in England not long ago, just a few weeks ago. And we are going to look at more and different galaxies in our next week.